Hey everyone, I've got a video for you here on section 1512. I encourage you to read it carefully and write notes and take what I have as little margin notes from me, and then ultimately I'll give you some problems to work on to wrap this whole thing into a nice package. So I know for many of you this is a bit of review, but we're going to talk about enzymes as catalysts in this section. Now, enzymes are biological catalysts. They're polypeptides or proteins that carry out very particular specific reactions. I do have here, although I need to say it was a huge deal when I was in grad school, when certain RNA molecules were also found to have catalytic properties. The initial theory of enzymes portrayed the relationship between the catalyst and the substrate as a lock and a key. This was actually proposed in the 1890s by Emil Fischer. He mistakenly thought that a rigid active site led to the remarkable specificity that enzymes exhibit. He thought because the lock was very, very precise for only a single reactant, then nothing else could react. For example, biochemists knew that some enzymes only hydrolyze peptides made up of L amino acids, and the others don't work. And again, it was a fit into a lock that people thought of. But we know that's not actually true. Enzymes, and all proteins for that matter, are quite flexible and exhibit cooperativity. The characteristics of having substrate binding alter the affinity for binding at other sites. Also, some enzymes are inactive if certain metal ions are not present, so that doesn't fit well with the lock and key mechanism. Although I decided not to do the theory part of this chapter, there is a little piece that I wanted to say for you. Let's see how the thermodynamics of something called transition state theory can help us understand more about enzyme kinetics. So it's important to realize that the presence of a catalyst lowers the Gibbs energy of activation. So if you can see in the diagram here, obviously the height of the barrier is what we're talking about. Now notice that it's not activation energy. That was something that Arrhenius talked about. Arrhenius is connected to, if you recall, when we plotted rate constants versus temperature, we had an exponential curve. Arrhenius's approach was basically empirical. He just fit a function to that curve. This is a little bit more rigorous. An enzyme forms an intermediate with a reactant and is released in the product forming step, but it does not affect the enthalpies or Gibbs energies of the reactants in the thermodynamics. I really should say that's not true. That's reactants for products. I think what I was trying to get at here is that I'll use my black arrow to indicate earlier parts of our textbook in thermo versus looking at the process of during the reaction is really what kinetics is about. So although we end up using thermodynamic terms like enthalpy and entropy, we will apply them to the transition state. So here's where I'm going to ask you to look a little bit more carefully at that rate constant equation. Here we see two thermodynamic contributions to the rate constant. Again, it seems ironic because we're talking about kinetics, but it is what it is. The enthalpy term, the delta H naught dagger, is approximately equal to the activation energy. So how strongly the reactants bond. We've already mentioned when we studied Arrhenius that changing the activation energy changes the rate constant. None of that is a surprise. What might be surprising to you is that this is not necessarily the whole story of how enzyme catalyst works. We will examine what is often the very important influence of the entropy of activation. Now you might recall when we talked about enthalpies, delta H's was often kilojoules per mole, and delta S's were usually joules per mole. So this might be a surprise, but let me try to convince you. So imagine a bimolecular reaction, okay? Two reactants coming together, and if they're not linear molecules, they can have a lot of disorder in them. If they're not linear molecules, they can have translational, rotational, and vibrational degrees of freedom. Each of these can store energy and contribute to the overall disorder of the molecule. Just think of a big old floppy protein, how much disorder you could have in that. The formation of an activated complex though, exhibits a net loss in entropy. If two big floppy molecules become one, what the calculations show in your text is you lose about 200 joules per K per mole because the translational and rotational entropies of this large molecule is just a little bit larger than an individual A or B. So if you have two molecules going to one, you're actually losing a lot of disorder. In other words, you're becoming more ordered. A negative value of delta S diminishes the value of the rate constant, which, if you think about it, defeats the purpose of a catalyst. Because we're saying here, a catalyst is providing an alternate mechanism, but this is a component of the catalyst-reactant interaction, which seems to be going against what we want. Now, this is important, though. For unimolecular reactions, there's very little entropy change. If you just have a molecule that's converting itself into a new arrangement, the delta S isn't going to be very bad. This means that if all things were equal from an enthalpy standpoint, because of this entropy difference, unimolecular reactions have faster rates. High-level theoretical study shows us that this difference can be on the order of 10 to the 10th. Let's look at this scheme and how it's a little different from that setup I just said. So in this scheme, an enzyme-substrate intermediate is formed, what we're calling ES here. Now, forces within the active site can align the substrate and the enzyme into a proper orientation, leading to the activated complex ES dagger. Since that step is unimolecular, the loss of entropy is small. In other words, the loss of translational and rotational entropy happened in the formation of ES through what's called an encounter. We talked about that a little bit when we were talking about diffusion-controlled experiments. The loss of entropy is compensated for by the binding energy. Once formed, ES dagger proceeds energetically downhill to the enzyme product intermediate, EP, and finally the product with the regeneration of the enzyme. So what this is saying here is that the unfavorable entropy term that's associated with the very first step is compensated by the enthalpy considerations. In other words, if E and S forms a nice tight bond, they could be a different, a Lewis acid base attraction or some new covalent bond. If they're forming a really strong bond, the fact that the entropy is unfavorable is not that big a deal. Having that two body to one body step happen first lowers the barrier for the internal reaction to occur that might be not as favorable from an enthalpy standpoint, and entropy is not going to take you in the wrong direction here. So this is very nuanced, but it is a important distinction in having the two body event happen first and then an internal sort of rearrangement to give ES dagger. All right. So now we're going to go in a direction that gets us to attach equations to match this mechanism. So the equations of enzyme kinetics. So for biochemists who study kinetics and want the purest possible numbers to compare one enzyme to another, they want initial rate data. So as you recall, when reactants come together and start making products, products can literally get in the way. And intermediates can exist that are sort of taking away when I'm talking about the purest possible information about data. So what biochemists want to do is they want to get initial rate data run for different substrate concentrations. That's what you're seeing here in figure 1522. In figure 1522, you see the rate of the reaction increases rapidly and linearly with the substrate at lower concentrations. So essentially what we're being told here is this is a roughly, you can see there's a bit of a curve in there, but early on there's a roughly linear relationship. Make this a little smaller. A roughly linear relationship for the low concentration substrate. At high concentrations of substrate, if all the enzyme is bound, the rate order essentially becomes 0 with respect to the substrate. So this part of the curve is essentially flat. It's irrelevant if you keep adding more substrate in. Now this type of curve, our friends down in the math department would call a rectangular hyperbola. The equation for this type of curve, again from the point of view of math, is this equation right here. Now I've thrown in the rate version. The rate is the y-axis, and the y-axis is going to include these constants. Now here's a proposed mechanism. A proposed mechanism would establish a pre-equilibrium. This is very similar to the kinetics problem I gave you on your exam. And then the decomposition that gives the enzyme out again with a product molecule. Now, this is unsatisfactory in a sense because if the production of product is the slow step, you've got K2 times the concentration of ES. But we know that ES is an intermediate, so that's unsatisfactory. I'm going to do the work on the next slide, but we're going to see that we can derive a rate law expression by doing a substitution. Now notice that 1565 and 1561 have the same form. Let's look at the two extremes that we have in figure 1522 to see what that does to our expression for the production of P. At low substrate concentrations, where S is much lower than this term Ks, I'll define Ks in a minute, we have a second order reaction. So if S is much smaller than Ks, essentially this goes away and you have a second order equation. First order in the original enzyme concentration and first order in the substrate. Alternatively, at high substrate concentrations, this term goes away, and you can see that the substrate goes away, and so now you just have a first order equation in the enzyme. So at these high concentrations again, all the enzyme molecules are complex. Again, this is the horizontal part of the curve. So I promised I'd show the math, and I thought I'd do that right now. So let's derive that equation without the intermediate. So I'm going to quickly draw here our mechanism again to see how we express this in terms of better measurable quantities. So he said the rate of the production of product here, the original, what we're calling the initial rate, that's what the little 0 means. We're right at the very beginning of this thing going. It's going to be K2 times the concentration of ES, but that's an intermediate. It makes us sad. Whoops. So we're going to do something a little different than we did in the beginning part of the chapter. Our biochemist friends want to do this. They're going to define a term called a dissociation constant. Notice what I'm doing. Again, it's similar to something you've seen in the past, but not exactly. Remember when we would take the forward reaction and equate it with the reverse reaction to get an expression for the intermediate? We're going to do something a little different. We're going to rearrange the same equation, but not to isolate ES. We're going to define this dissociation constant term. Notice how it's the inverse of an equilibrium constant that you may have learned in general chem, which has the products over reactants. This one really has the reactants over the products. It's going to be convenient for us to set up my total original enzyme concentration as being equivalent to the sum of free enzyme and complexed enzyme. So I'm going to plug that into my dissociation constant expression in order to get what I have here. So I rearrange that. And then I'm going to solve for ES. I'm going to ask you to do that. I'm going to actually give you a different color here. I think it took me 3 or 4 steps. But when I got done to isolate ES, it's equivalent to the original enzyme concentration times substrate over Ks plus S. Okay. Now, and I'm loving my colors today, I can take my substitution for ES and put it back into there. So our ultimate goal was to do what we always do, which is make a substitution for an intermediate. But for reasons that are easier experimentally, we wanted to get it in terms of the original enzyme concentration. And so that's what we did. So if we plug that back in, we get this expression for what we were originally after, which is my rate of the production of my product. K2 E naught S, Ks plus S. So the rate is going to be proportional to the total concentration of the enzyme. Now again, this is the same form as the curve. So it seems to verify the mechanism that got us here. Except with the substitution that the A term is equal to K2 times the enzyme concentration, and B is equal to my dissociation constant. At low concentrations, we have a second order reaction, and at high concentrations we have a first order reaction. So take a look at that. All right, now I want to state again to keep in mind that the assumption that a rapid equilibrium first step is an important part of that mechanism. Here I want to mention that everything we just did, the fact that we mimicked that hyperbola, does not prove that mechanism, or you cannot prove a mechanism by running experiments. You can only verify a mechanism. I'm being subtle here, but there is a difference. We'll soon see that an alternative view of what is happening at the molecular level is actually going to yield the same curve. I want to mention that term again that biochemists claim as their own. If you're not a biochemist, this may seem a little odd, but instead of writing the familiar equilibrium constant that normal chemists use, and I'm kind of trolling Dr. Carnegie here a little bit, she's always saying biochemists are chemists too. But biochemists have defined their own term. And it actually makes some sense if you think about the point of view. Is the dissociation constant Ks is really a statement about the binding. If you have a large value of a dissociation constant, it means that that substrate isn't binding very well to the enzyme. And I think that that's something that's important to understanding what's going on in a biochemical reaction. Another vocabulary piece is that in the horizontal part of the hyperbola, when all the enzyme molecules are complex I mentioned, you can call that rate is called Vmax, or the maximum rate. That's going to be equal to that part of the curve that's first order in the original enzyme concentration. Now something interesting happens to our equation, the big equation before I applied these conditions to it, when the substrate concentration is exactly equal to the dissociation constant. You can do some cancellations, and you find out that that's exactly half the Vmax. So what that means is that the dissociation constant equals the concentration of the substrate when the initial rate is half its maximum value. Okay. Now I mentioned to you earlier that you can get the same curve by assuming a little bit of a subtle difference in what's happening at the mechanism. instead of assuming the pre-equilibrium, I forgot to put my little extra quotes in there, mentioned earlier, comma, Briggs and Haldane applied the technique of the steady state that we've seen before to generate the hyperbolic shape of 1522. We saw this earlier in the chapter when we had a later slow step and we used the earlier equilibria to make assumptions in order to make a substitution for the intermediate. I also told you, and we used the example of the chain reaction, that an alternative approach is to use the steady state approximation. That's when you take something like an intermediate, set its change with respect to time equal to 0, and then you add and subtract all the components that use that intermediate, whether you're creating the intermediate or losing the intermediate. Taken together, their change is equal to 0. So I think I wrote down for myself in my notes where this was. Yeah, I'm going to ask you to review 688 to 690. That was the explanation of the curve when we applied the steady state approximation. But here you can see it. It's a very good approximation. The magenta line, the enzyme substrate complex, that's a pretty flat line for a good period of time. So during that purple-pink region, this assumption about the steady state is essentially true. And you can go through and generate this equation. Now we have a little bit of a difference in the steady state kinetics. We don't have the dissociation constant. We have something called the Michaelis constant. Michaelis constant is a combination of all the little k's that ultimately give us our mechanism. So comparing the Michaelis constant to the dissociation constant, we see they have a similar dependence on substrate, but they're not equal to each other unless the K2 step is very, very, very slow. Otherwise, if they're in the same ballpark, they are different terms. And so, and because the original enzyme concentration is Vmax over K2, we get this version. So in principle, we're getting the same curve we had before. In principle, a plot such as the one on the left can help us determine Vmax and the Michaelis constant, but in practice it's a little bit more difficult because of the difficulty in determining the asymptotic value of Vmax at very high substrate concentrations. Once you get these very large concentrations, it can be very, very difficult to find out what value this curve is approaching, and so you're not going to get a lot of accuracy on the Vmax. We would like the Vmax value, though. That's the highest efficiency of an enzyme, and so we're going to have to be a little bit more. Okay, what I'm using this slide for is just to show you the math of how we can get an expression that gives the curved hyperbola without assuming the initial pre-equilibrium. So it's the same mechanism in a way. It isn't that the K2 is so slow that you have the first two arrows in equilibrium, it's just that they're kind of all going on at the same time. We're going to do a lot of the same math, and ultimately the goal is to get an expression for the enzyme substrate complex that can get us a rate law expression. So this is the steady state approximation again. There are two different steps that consume ES and one step that creates ES, and that's what gives us our setup here. We're going to make the substitution that it's going to be easier to have an expression that has the initial enzyme concentration in our final answer. So we make this substitution here, similar to what we did on the previous slide. And then we're going to rearrange this guy until we get an expression for ES. Actually, I made a mistake here. Right here, this is the concentration of ES. Okay, now this guy can go into my rate loss step. And so I'm going to get that the initial rate is equal to K2, K1, initial enzyme concentration times the substrate. And I've got three terms down here. K1 S plus K minus 1 plus K2. Now this is the way that I think it comes out. If you multiply the top and the bottom by 1 over K1, you can do some cancellation. And our rate law expression turns into this. Simplifies it a little bit. We only have 3 terms in the top, and I end up having this collection of k's in the bottom. And that's what we're calling the Michaelis constant. Michaelis constant is a mixture of these 3 k's that we've talked about for this whole page. This is 1569. So if we insert this Michaelis constant, and also what we know about this expression, which we defined as Vmax on the previous slide, the initial rate is going to be Vmax times the substrate concentration over the Michaelis constant plus the substrate concentration. There's some other things you could do with this under different conditions in the textbook, and I'll leave you for that. But my point here is to show you that we're getting an equation that looks very much like the hyperbola with essentially a different, although nuanced, different mechanism. Now, getting data for this involves some graphing. As we said, it can be very difficult to get accurate values of Vmax in an experimental setting, but getting this for reasonable experimental data comes to, okay, Lineweaver and Burke. So this is a rearrangement of that rate equation I had on the previous slide. Let me rewrite that. I should have had that here already. And essentially what we're going to do is to invert this guy. And then separate it out. And you can see that I am reproducing what I have above. Poor planning. Okay, and now you could see how you get a straight line. If you're going to plot 1 over the initial rate times 1 over substrate concentration, and the slope is that ratio, the intercept is 1 over Vmax. Now, you can get a straight line. There's a bit of a disadvantage here we're told about. It compresses data points at high concentrations into a small range, and that's going to affect your accuracy. It emphasizes the points at small concentrations more, which again are harder to measure. So there's many alternatives. The one that the textbook looks at is called Eadie-Hofstee plot, which takes the equation that I just showed you, and it multiplies by V naught times Vmax. If you do that, a lot of biochemists prefer this plot, where you're going to plot initial rate versus x is, whoops, it's a minus sign there, I just saw that. The slope is minus the Michaelis constant, and the x is the rate over the concentration. You could have fun with these in your homework. And I just remember there's one more slide. This is going to be some reading and some notes and maybe some Google work. What I did is I took the 2 pages at the end and I wrote some questions out of here. So do your best to answer these with the textbook material, but also go beyond that. If you could add to my knowledge on some of these questions, if you have your biochem book, or just do some Googling. Write some good answers on these, and maybe we could talk about those at some point. The first thing I'm going to start working on, though, is these homework problems. I'm going to work on end of chapter questions 41 through 49. They are what we talk about in our Zoom sessions this week. So good luck. I hope everybody's doing well, and we'll talk soon.